Welcome. Yeah, so first and foremost, as always, thank you, Lord Christ, you're amazing. And second is I already have a video series on optimization, but I found this really neat problem, and so I thought I'd make a bonus example. Yeah? Okay, cool. So the question is this, which is you have cone of diameter 8, so the base diameter of the cone is 8 and the height of the cone is 12. And what we're tasked with is figuring out the biggest cylinder we can fit in there, biggest by volume. Yeah? Okay, cool. So how do we do this? Well, first, whenever you're doing an optimization question, you need to figure out what it is that you're trying to maximize or minimize. So in this case, we're trying to maximize the volume of the cone. So we're trying to maximize the volume of the cylinder. I misspoke. All right, so volume of a cylinder is given by the base area, which is pi r squared, times height. If your solid has uniform cross sections horizontally, that is that like all of the horizontal cross sections of your solid are the same, which is the case in a cylinder, they're all circles of the same radius, then the volume is always like, well, one of those cross sectional areas, pi r squared times height. Okay. Now, the only problem is that this volume equation has two variables, r and h. Now, if we're doing multivariable calculus, we can use the method of Lagrange multipliers to still be able to maximize a function of two variables. But since this problem is intended for single variable calculus, we either need to figure out how to get rid of the r or how to get rid of the h, and obviously using relationships contained in this visual, right? Okay, so instrumental to this turns out to be similar triangles. That's always the case whenever you're dealing with a cone and optimization or related rates in Calc 1. All right, so let me draw the triangle Z of interest because they're similar triangles. So it's two triangles I'm talking about. So what are they? All right, well, so let's do it with this. Well, let's draw a triangle and then a triangle within the triangle, which will give us similar triangles. So this triangle I just drew is a triangle that is in the cone, and that's this triangle right here. I could have used a triangle on the left, but this triangle on the right is nicely labeled up, and we know that the diameter is 8 and the base of the cone, so that means this little bit is 4. Got it. This is 4. And we're told that the height of the cone is 12, so this bit is 12. Got it. And then we could see that we've got a horizontal line here, which is parallel to this line. And so we've got this situation right here. We've got an R horizontally drawn. So this is R. Okay, cool. So the two similar triangles that we're talking about is this little fella at the top and the big right triangle that contains it. So they're both right triangles, right? Because, well, this is a right angle and this is parallel to this, so that's got to be a right angle also. Okay, so then we should figure out what this length is so that we could use proportionality of similar triangles. Since from here to here is 12, and from here to here is h, where h is the height of the cylinder, we're saying that this bit is h, and we already know from here to here is 12, so this bit has got to be 12 minus h. Got it. Okay, so I don't know if you could see that. Let me write it a bit. 12 minus h, right? Okay, got it. And so then when we write the proportions given by similar triangles, we could write that 12 minus h, this to r, so 12 minus h to r has to be in equal proportion to the corresponding side to this on the big triangle is this, which is 12, right? To this is the corresponding side to r on the little guy, on the little triangle. It corresponds to 4 on the big triangle. So we write that. Okay, now 12 over 4 is like 3, right? So we could just write 3. So this works out real nice. And now we have to think, do we want to replace r or h with the relationship between r and h that exists here? Let's see. So if we multiply by r on both sides, we'd say 12 minus h is equal to 3r. So we see that if we want to replace r here, we have to next divide by 3 on both sides. And so that would introduce a denominator when we substitute for r, and we really don't like that. So we'd be able to get r in terms of h if we divide by 3 on both sides of this, but then we'd have a denominator in our replacement for r. I don't want that. So what we're going to do is add h to both sides and then subtract 3r from both sides. So we're going to write that 12 minus 3r is equal to h. Got it. And also notice that here we could factor out a 3 and write h is 3 times 4 minus r. Got it. Maybe this is helpful, the factored version. Okay, so this, these similar triangles were only useful insofar as we create this relationship, but now we're done with them, so we get rid of that. And now we're able to get the volume of the cylinder, which is what we're trying to maximize. We're able to get it all in terms of a single variable, and we really like that. So v is a function of r. So v of r is going to be pi times r squared, and then h we see is 3, so I'll write the 3 here, times 4 minus r. Got it. Okay, cool. And for the purpose of taking derivatives, we probably want to distribute this r squared, and so we're going to write v of r is equal to 3 and then pi times r squared times 4, so that's actually 12 pi and then r squared, and then minus what? Minus 3 pi r cubed, right? 3 pi r cubed. Got it. Okay, cool. So now what? Well, as with every optimization question, once we figure out the function we're trying to optimize, which is maximize or minimize, and we get it into one variable, we take the derivative. So we're going to be like v prime of r is equal to, well, that's going to be 24 pi r, right? I'm taking derivative now with respect to r, so 24 pi r, and then minus 9 pi r squared. Got it. What do we do once we find the derivative? We set it equal to 0, seeking critical numbers, right? So when we set this equal to 0, I'll just get rid of this and write a 0 right here, less writing, right? Then we could add 9 pi r squared to both sides, so what we're going to get is 9 pi r squared is equal to that. And then now we want to solve this, so we turn it into this, right? Okay, and then what could we factor out? We could factor out a 3 pi, right? And so then we could write 3r squared, and then minus what? Minus 8. Sorry, did I factor out too much? No, but minus 8r, right? Okay, equals 0. And next we're going to divide both sides by 3 pi to simplify our equation. So once I divide both sides by 3 pi, that's what I'm going to get. And from this, I'm going to factor out an r. So r times, and then it's going to be 3r minus 8 equals 0. Got it. So the two r's that solve this equation, and so the dimensions of r that will maximize the volume of our cylinder, are going to be r equals 0, which we know doesn't work. Okay, and then otherwise r equals 8 over 3. Okay, cool. Now, these questions are, well, I guess because the universe is mathematical, always designed, or they always work out so that whatever is supposed to be maximizing does maximize. So we can do a number line test and put this number 8 over 3, what's that, like 2 and change, to see in fact that it maximizes v of r, right? But it will invariably do that. So if this is like, let's say 2 and this is 3 on the number line, then 8/3 is somewhere closer to 3, right? So we put 8/3 right here. Got it. Now what we need to do to show that this is an r value that will maximize v is, well, this number line is for v prime, so we test numbers to the left and right of 8/3 and v prime. And I erased v prime, but I could do it again. It's not that big a deal. V prime is equal to what? 24 pi and then minus 9 pi r squared. So if we test the number to the left, say 2, and it's 24 pi r, my bad. If we test a number to the left of 8/3, which is 2, and to v prime of 2 is going to be 24 pi times 2, that's 48 pi. right, we're going to get 48 pi, and then minus 9 pi times 2 squared. What's that? 9 pi times 4, that's 36 pi. And so we could clearly see that this is greater than 0. So v prime is positive to the left of 8/3. But if we plug in 3, that is, if we calculate v prime of 3, what we're going to get is 24 pi times 3. What's 24 times 3? I believe 72. So we're going to get 72 pi minus, and then 9 pi times 3 squared. Okay, so that's 9 pi times 9. That's minus 81 pi. Clearly, this is less than 0, so it's minus on that part. But if we go from positive slope to negative slope, whatever number is here maximizes our function. So v is maximized by the r value 8/3. Got it. Of course, since we already had a relationship between r and h that we wrote earlier, which is h is 3 times r minus 4, I believe. Yeah, but whatever it was, you can plug in this r value to find h, and of course once you have r and h, you could say what the maximal volume is, but I think I have done enough, don't you? So I'm done here. I hope you enjoyed this. Keep watching. Take care.